let's begin the afternoon session. So our first speaker is Stefan Milius, who will talk about one-Eilenberg theorem.
All right, so first of all, I'd like to thank the organizers for inviting me and giving me the chance to give this talk here. And this is joint work with several people, namely Jerzy Adamek, Yangting Chen, and Henning Urbat. And now with such a title, one is of course asking for trouble. So perhaps we should have replaced all by many of them, or we should have put it two words in front, but where would be the fun in that? I still managed to put a question mark here as opposed to in the program. Yes, and this is what the talk is about. And it's in category theory, and I think it's one of the examples where category theory can unify things that are in the literature and that look the same, but we can formally say why they are the same, and this might save work and trouble for many people. Okay, so what this is about is algebraic language theory. So that is the study of the behavior of finite machines, for example, deterministic automata, with algebraic structures. So in the classical case, one looks at monoids. Now, coming from a category theoretic background, we saw all these different kinds of algebraic structures with which you study different kinds of behaviors, or sometimes the same behavior. And we were asking ourselves, okay, so is there a unifying view for this? And actually, building blocks to study these things are there in category theory. So if we want to approach automata, like this little guy here, from a categorical perspective, there's a lot to build on. So for example, automatas can be captured via algebras and coalgebras. So algebras, this goes way back to the 70s to work by Joe Goguen or Arbib and Menis. Coalgebras is a bit more recent, let's say the last 15 to 20 years. And their languages essentially appear via initial algebras and final coalgebras. So being characterized by universal property. Algebra, of course, is for category theory, it's a classical subject going back to Liouville theories and the study of monads. So this is what we're going to look at. So our goal is kind of a categorical algebraic language theory using monads. And in this talk, I'm going to focus on one theorem from algebraic language theory, and that's Eilenberg's variety theorem, which states that something called varieties of languages are in one-to-one correspondence with pseudo-varieties of monoids. So actually that's an isomorphism of lattices. So what are these things? So pseudo-varieties of monoids are almost like Birkhoff varieties of monoids, except that you put the word finite in two places. So first of all, you consider finite monoids, and a pseudo-variety is a class of finite monoids that's closed under a quotient, submonoids, and finite products. So the two occurrences of finite is the difference to Birkhoff varieties. Varieties of languages, on the other hand, are classes of regular languages. Here that's stratified by fixing alphabet, but is ranging over all alphabets. And these classes are supposed to be closed under the Boolean operations, under language derivatives, and under pre-images of monoid morphisms between free monads. So if you've got monoid morphism from delta star to sigma star, and a language L in V sigma here, then its pre-image is in V delta. Okay, so that's Eilenberg's classical variety theorem. And now, 40 years later, if you look through the literature, you find more than a dozen theorems that look similar. So there are other Eilenberg-type theorems. On the one hand, ones that consider weaker closure properties, but still talk about regular languages. So for example, an ordered one by Jean-Henri Pin, one for, based on joint semilattices by Pollack, Reutenauer's theorem, which is actually more general in some sense also, because it's not just about regular languages, it's about weighted languages. One could consider fewer monoid morphisms than all between free monoids, or more recently, one could consider what's called local Eilenberg-type correspondences, where you fix one alphabet and then you don't consider the pre-image property. So this is from work by Gerke, Serge Grigoriev, and Jean-Ric Pin. And on the other hand, there are Eilenberg-type correspondences, probably more than the ones that are listed here, for other finite machine behaviors. So I mentioned weighted languages already. One could look at infinite words, and there's also an ordered version for this. One could look at ordered words, ranked trees, binary trees, and very recently people have looked at cost functions, and we are particularly happy that in the end we're going to include this as an application, because in their paper they actually ask, so there are these general methods, and it would be nice if this could be covered, and the answer is yes, we can do this. So this talk is going to be about a general variety theorem that covers all these as instances. Right, so, and what's the big picture? So what are the two main ingredients that you need for such a general variety theorem? Well, it's monads and dualities. Well, it's of course a bit oversimplifying, but it's a catchy equation here. So why monads? Now, on the one hand, you want to generalize from monoids to other algebraic structures recognizing machine behaviors. And other algebraic structures, categorically, you can capture by monads. And so they are used to model the type of languages and the algebras recognizing them. And that's not actually our idea. This is an idea of Bojancic, published last year, and there's also a longer technical report on arXiv on this. So that's one side, using monads. The other is duality kind of plays in the background if you want to relate varieties of languages and pseudo-varieties of monoids. And this is, I think, very clear for the first time in Gerke, Grigoriev, and Pin's paper from ICALP 2008. And we've been inspired by that and have worked on general Eilenberg theorems and Reiterman theorems since then, and so this occurs also in our work. But duality in language theory goes back further, at least to Pippinger's paper in '97. One other thing I should say here is if you compare Bojancic works and ours, it generalizes Eilenberg-type correspondences in kind of two orthogonal directions. So whereas in Mikolai's work, one has monads, they're all on sets or sorted sets, while in our work, we have a general Eilenberg theorem previously that works on more general categories, but it always considers monoids. So then, of course, if you look at this, you ask yourself, okay, what's the common roof? Monads on sets, monoids in arbitrary categories. The common roof should be monads on an arbitrary category. So that's what we're going to look at. So how do monads model the type of languages in algebras? So we're going to start with a monad on a locally finite variety. So it's kind of an algebraic theory on an algebraic theory, but don't worry, in most instances, this D here is going to be just sets or posets. And for some applications, one needs sorted sets or vector spaces. I'm also suppressing the sorted setting here, and also the ordered. It could be an ordered variety. So that's in the paper. In the talk, I'm just going to look at this locally finite variety. There's going to be a two-sorted example soon. All right, so that's what's fixed. And then one can give, in this setting, a very general definition of what a language is. Namely, it's just a morphism from a free algebra on some object of D, which we think of as an alphabet, to some object O of outputs.
So D is a category of some general kind? I mean, when you say locally finite variety...
Aha. So that means it's a finite... free algebras on finite sets are finite. So it's a variety with this property.
Based on set? Based
on set. Yeah. Or poset, if it's an ordered. So those are the two cases we consider. Mm-hmm. So, and with this general definition of language, you of course can capture ordinary languages by just taking the free monoid monad on sets, so T sigma sigma star, and O to be the two-element set. So then that's just a predicate on sigma star, which is a language, like such a morphism. if you want to do something more fancy, like languages of finite and infinite words, you immediately need a two-sorted setting. And so there, your monad, what it does, well, here's just said what it does if you take a two-sorted set with sigma and empty set in the second sort. It's doing this. So that's the monad of 3 omega semigroups, and as the output object here, you take 2 elements in both sorts. And then it turns out that the languages are just the languages of finite and infinite words. And then for other examples, you have to instantiate the data differently. So for example, for weighted languages, you take vector spaces. For tree languages, you need 3 sorted sets. For cost functions, you need posets, and so on and so forth. I can't really show you all the more than 12 examples in detail here. And also language recognition is kind of straightforward, because you say a language like this, morphism from T sigma to O, is recognizable by algebra if it factors through some finite quotient algebra. So here, this diagram states that the language is recognized by the algebra A. So this needs to be a finite quotient of T sigma. And again, if you look at the instances, this is exactly the classical recognition in this example here of languages by finite monoids. So the recognizable languages are exactly the classical regular languages. If you look at this other example, you get exactly the regular languages of finite and infinite words. So it seems to work, let's say, by judging from these 2 examples. All right, so this is how monads come into the picture. What about duality? Now, if you look at the classical Eilenberg theorem, then somehow stone duality plays a role in the background. One can see it essentially by looking at Pippinger's result from 97. So first of all, here we have stone duality. So we have the category of stone spaces, which is dually equivalent to Boolean algebras opposite. So it's dually equivalent to Boolean algebras. What's also playing a role for us that this is the profinite completion of finite sets. And now there's the stone space of profinite words, which is the inverse limit of all finite quotient monoids of sigma star. And this turns out to be dual to the regular languages. And this is essentially a glimpse of this Eilenberg correspondence appearing, I would say. And what's important for us is that this correspondence, or this dual correspondence between the profinite monoid and the regular languages, this works in this general setting for monads. So it generalizes from sigma star to arbitrary monads. Okay, let's look at this. So we have our monad on D as before, and now we need some more. We need another locally finite variety, so that's another assumption that we have to make, such that actually a bit more than this here, what we need is that the finite algebras in C are dually equivalent to the finite algebras in D, and then this follows. So if you take the pro-completion of the finite algebras in D, this D hat, this becomes dually equivalent to C. So that's kind of what we need. And then instances of this is, of course, stone duality, as we've seen. So you've got Boolean algebras here, and stone spaces here, and finite sets here. You could take Priestley duality, or you could take vector spaces as C and D, and then you get stone vector spaces here in the middle. And there's some other instances. The role of this free profinite monoid is now played by doing the same construction that we saw before, but now with T algebra. So you take the inverse limit of all finite quotient algebras of a free algebra on sigma, and let's call it T hat sigma, and this is going to be the free profinite T algebra. Actually, this becomes a monad on D hat, which we call the profinite monad, and it's a thing we have seen yesterday in Daniela's talk. Namely, that's this co-density monad that she showed us. For those category aficionados among you. Now this output object here, this is not a parameter you put, but it's somehow now, once you chose this duality here on the finite level, it's somehow forced upon you what you should take. Namely, you should take the dual of the free one-generated algebra in C. This must be your output object, otherwise the rest is not working. But it's the right thing in the examples. And now what you can prove is, and this is a little theorem you have to show, is that the recognizable languages are just isomorphic on one-to-one correspondence with the morphisms in this pro-completion D hat from T hat sigma to O. So previously, languages were morphisms from T sigma to O, factorizing through some finite algebra, and this somehow then disappears if you talk about profinite. And then going on, using the duality, one sees that, well, since O is dual to 1, and you have to turn around things here, so this is the same as the C morphisms from 1 to the dual of T hat sigma, and so that's the essentially the elements of the dual of T hat sigma. So what this says is that the recognizable languages can be viewed as an object in C here. And this is now kind of a general version of this regular languages are dual to the free profinite monoid that we see in our setting. And then this T hat is actually very important for the proofs, but it's not going to reappear in the talk from now on. All right, so back to the statement of Eilenberg's variety theorem. So there it is. So now I want to massage this and replace bits and pieces and get to the statement of the general Eilenberg theorem. So first of all, monoids, of course, are going to be replaced by T algebras, well, in the year by 40 years later. Because that's easy. All the closure properties here, quotients, subalgebras, and finite products, they make sense for T algebras. It's just what you know. On the left-hand side, it's going to be a bit more difficult. So first of all, saying a subset of the regular languages closed under Boolean operations. What's that supposed to be? So we've replaced stone duality, so Boolean algebras and stone spaces, by something more abstract. So what we should get is what corresponded to the Boolean algebra. So that's this category C here. And, well, some subset closed under something is just a sub-object. So V sigma is going to be a sub-object of the recognizable languages considered as an object in C, as we can do, as I just showed you before. And then closed under these two things. Now, of these two things, the second one is fairly straightforward, or it's straightforward. You, again, replace just monoid by T algebra and morphisms between free monoids by morphisms between T algebras, observing that pre-images you get by precomposing with such a morphism. So that's pretty straightforward. Now, the important bit is what happens to the derivatives, and that's really in some sense, the crux of the matter. So let's look at the classical Eilenberg theorem again for a while. So there we have these derivatives on both sides, and they correspond to unary operations on sigma star given by words or single letters composed on both sides of a word. And now the language derivative of L is just given by taking L as a predicate and composing it with the unary operation. Okay, something similar is what we need. And then the important observation here is that from these unary operations, you can actually recover the monoid structure of quotients of sigma star. So if you have any surjective map from sigma star, then this carries a quotient monoid if you have a lifting property with respect to all these unary operations. So namely, every one of these unary operations lifts to the quotient. And this is what we need, and this is what we're going to use as the definition now. So what we need is that our monad is not just any monad whatsoever, but we also need a good unary presentation on it. So that's a bunch of unary operations such that any quotient in this category D carries a quotient T algebra if and only if all these unary operations lived along E. So that's exactly the same property. And now, of course, it's true that if you have, for example, a finitary monad on sets, there always is such a unary representation, which you can construct, it's canonical, but it's probably useless because it's too big and unwieldy. So this is why we decided to make this another parameter of the framework. And this is where I think for automata theorists the challenge is to come up with such a presentation that's good. But for what we are after, it's going to be a parameter. And with the help of such a unary representation, it's now easy to say what is the derivative. Because if you have a language and a unary operation, you just do precomposition, and that's your derived language. So coming back to the statement of the general Eilenberg theorem, it's now easy to say closed under derivatives. You just plug in what I just said. So we must have this unary representation. Then for all unary operations, if you have L in V sigma, its derivative is also in V sigma. Okay, so there is the generalized Eilenberg variety theorem. And now, how to prove this? Well, you dualize. Of course, this is oversimplifying because obviously, I mean, if you look at these two things, they're not obviously dual. So there is some beautiful, non-trivial work going on in the background, but that's in the paper, and I won't tell you about this. But at the core, there is a dualization going on. So actually, there's something in between here, which is profinite theories, and this is where the codensity monad plays a role. And so you first go from the pseudo varieties to what we call profinite theories, and then you dualize something, and then you come back to varieties of languages. All right, so applications. So as I said, we have this duality on the finite level, the monad, the unary representation, they're all parameters. And depending on applications, there might be other stuff. And there might be some properties that these things have to satisfy. That's all in the paper. I don't want to go into this. Anyway, then you get out of this theorem more than a dozen variety theorems that are known in the literature, namely all of them that I listed before. So all these are instances. And you also get new results out of this. For example, I mentioned this local Eilenberg theorem of Gerke, Grigoriev, and Pin. And since the proof is kind of modular in the sense that we establish a local Eilenberg theorem and then we kind of beef it up to the real thing, the full general Eilenberg variety theorem. So we get local versions for all of these more than a dozen theorems as well. And most of them are not known, so they're new. All right, that's essentially it. So the take-home message from this talk is that Eilenberg is essentially monads plus dualities. So what we've seen is a categorical approach to algebraic language theories using monads. And so we joined previous work by Bojancic and by ourselves in this work here. We saw that we get this general Eilenberg theorem with many applications. To be quite honest, what it does, I mean, it doesn't take away all the work from people interested in automata theory. It somehow isolates the common algebraic parts of these proofs, of these Eilenberg-type correspondences. So there's always non-trivial work that lies in finding the right monad. So if you start with some kind of finite machine behaviors, you still have to find the right algebras. And you still have to find, once you have the monad, a good unary representation, because this will correspond to the derivatives that you're looking at. But we think that the whole framework that we have kind of helps, because once you have that, the rest is kind of automatic. And so maybe it helps to focus on the things that really matter. There's further work, that's not future work, that's actually something that we've done. There's also a general Reiterman theorem, which relates pseudo-varieties that we saw on the right-hand side to profinite equations. which are kind of a syntactic way to specify these pseudo-varieties rather than characterizing them by closure properties. So that's fairly recent. Then there's the question, what about non-regular languages? Because recently, and some years ago, there's work where Eilenberg-type correspondences were proved for non-regular languages. And they currently wouldn't be direct instances of what we have, but we're really convinced that the kind of methods we have would allow us to get a theorem that would cover them as well. So this is why this question mark is small and only in gray. So in particular, I think Henning has already written this up. Then speculatively, one could be interested in a nominal version, so an Eilenberg theorem for data languages. But this is, so there are two question marks because we think it's quite hard. So there's nominal stone duality in the work of Gabay, Litak, and Petrishan, but it's very unclear how to get an Eilenberg-type correspondence. And then maybe something like monadic second-order logic for a monad, and I don't know what that should be. Okay, thanks very much.
Questions?
Maybe a comment. One of the things is monadic second-order logic for monad. So in my paper, there is a proposal for that, which covers monadic second-order logic in all known examples.
That's for the set.
Yeah,
Yeah.
that's where the known examples live. And another, this one is a question, is you have this unary presentation. So when I was trying to prove that Eilenberg theorem in monads, I used a notion of derivative in the sense of there's two actual alternative definitions. One of them is a derivative of a language is anything recognized by its syntactic algebra. And then you don't need to specify it's a parameter; it's just there. How does that? How does that extend to?
But this is you use the polynomials. Is that?
So that's the other way.
That's the other way.
The polynomials are maybe don't extend so clearly to categories beyond sets, so I didn't want to mention them. But the other one, I think it does. So.
Yeah, but does it instantiate to the theorems that you know?
Yes.
Okay, so then I would have to look more closely at this again. Yeah. But so in our setting, this was precisely the reason to have these unit representations, so that you have something that corresponds exactly to the derivatives you see in applications.
So that's the case.
Other questions? So let's thank